Okay, so this next is 16.4. It's called Green's theorem. And this one is kind of a little baby theorem compared to what it turns into, which eventually turns into Stokes' theorem. And I think we can work it to turn into the divergence theorem, basically two-dimensional versions of what is called Stokes' theorem, very important theorem in physics. And then also Green's theorem can be converted into a two-dimensional version of the divergence theorem. So we'll be talking about all of that. Okay, so I want to go ahead and set this up. So I'm going to put a counterclockwise orientation on C. Okay, so that's C. Inside will be a region that we'll call R. So this is a two-dimensional theorem. Stokes' theorem will be the three-dimensional version of this. But that doesn't come up to like 16.9 or 16.8. So we've got a ways to go for there. Okay, so let's say let f of x, y be p of x, y, q of x, y. Like that. And we want these to be differentiable in R. Okay, this curve C, we want it to be continuous. Closed, piecewise continuous, sorry, piecewise smooth, so it can have sharp corners on it. It's smooth in pieces is the idea. It can have corners on it, but not an infinite number of them. And simple. And simple means it doesn't cross itself. It doesn't intersect itself, if you like. Okay. Okay, so Green's theorem, let me check something real quick. I left something out, so I gotta look it up real quick. Continuous partial derivatives. Okay, so this thing right here with P and Q having continuous partial derivatives, and I mean just first partials, over the open region, any open region containing R. Then here's Green's theorem. It just says that, that the work integral along this curve C, and notice I'm going to put an orientation on the curve. So that's curve C with counterclockwise orientation of f dot dr, that's just a work integral, is double integral over the region inside of qx minus py. dA. So that converts a line integral into a double integral. Now, there's a couple of versions of f dot dr. So f dot dr, this is just kind of a note here. So f dot dr you can write as a line integral of f, which is pq. And sometimes we think of dr as just having differentials dx and dy. And that's the same thing as a line integral here of p with the differential of dx plus q times the differential of dy. Okay, so there's just different ways of expressing what f dot dr is. These are all the same. Okay. And sometimes it's almost more common to express greens this way. So greens can be expressed as this thing, line integral counterclockwise orientation of a closed curve C of pdx plus qdy equals the double integral of qx minus py dA, like that. Okay, any questions? Okay, any questions? All right, we have to do examples, but you get treated with the proof of this theorem. So here it comes. Okay, so we're going to assume that it's a convex region. So we're going to assume R is convex. and both type 1 and type 2. Type 1 I called vertically simple. And type 2, which is horizontally simple. Okay. So I'm going to go ahead and first of all create this region R as a convex region, like that. And let's go ahead and break it up like this. We'll have a top curve. And a bottom curve. See if I can't do it. I'll try one more time. Okay, so that's pretty good. So on the bottom, I'm going to have y equals f1 of x. And on the top, I'm going to have y equals f2 of x. Okay. I can do that because I know this is vertically simple. But it's also horizontally simple, so I can do a left curve and a right curve as well. So here we go. So I'm going to do the left curve here in green. Let's see if I can pull it off. Like that. So that's going to be x equals g1 of y. Like that. And then a right curve. Now I need another color. So I guess I can do blue. So the blue one is x equals g2 of y. And basically, curve C can be divided up two different ways. Okay. So like that. So again, this is curve C. Now, what I want to do is do the double integral side of Green's theorem. So Green's theorem looks at this double integral here and shows that you can write it as this line integral. So that's what I'm going to try and do. Okay, so we'll take the double integral side, and since that's just a little easier. And this is a weird theorem, but when you see the proof, it's just sort of obvious. So, and you just kind of follow your nose on this thing. You go, okay, there's a double integral. And obviously I can write that as two integrals. So let's do that. Okay, so I have a double integral here of qx, and that'll be dA, minus another double integral of py, and that's dA, and both of these are over region R. Okay. Okay, any questions? Okay, and I guess I should have put a coordinate system on this darn thing, because I'm going to need lower values for x. I'm going to need boundaries on x and on y. So I'll worry about that in just a second. You guys are going to be so angry at me. More than usual. So here's what I really wanted was an x coordinate system. Okay, like that. So that I could say that x goes from A to B. And then y goes from C to D. Okay. I'm sorry. All right, so then if you look at these double integrals, all of this sort of makes sense to do the following. Because I'm doing qx, it makes sense. That's a derivative with respect to x. Why don't we integrate with respect to x first? And so then we'll do y after that. And then it makes sense on the next one, because it's py, the derivative of p with respect to y, why not do the antiderivative with respect to y first and then x then? Okay. Now on the first one, we need limits on x for q. So x would go from g1 of y to g2 of y. And then y would go from A to B. Sorry, from C to D, my bad. Like that. And then on the other one, we're doing dy first. So the lower limit on y is f1 of x to f2 of x. Like that. And then, of course, x goes from A to B. Like that. Now, again, these are derivatives with corresponding antiderivatives. So it makes sense to just evaluate directly. So you can see how these turn into single integrals. Remember, Green's theorem says that the double integral can be written as a single integral over a curve. So, and probably easier to express it this way, the double integral being written as really two single integrals here. Okay, so you can kind of see how this is all playing out. I don't know how it turns into a line integral yet, but we'll see how that plays out. Okay, actually, it's not that big of a deal. You can almost see it here. Let's go on. So the first integral from C to D is going to just be Q. Okay, because I've taken an antiderivative of Qx with the dx, so it's just going to be Q of xy. Now these are limits on x, so the lower limit is going to have x going from g1 of y to g2 of y. Okay, and that'll be dy. So there's the q dy, right? And is that what we're supposed to have up here? A q dy up here? And then the other part will be the p dx. So minus the next piece, which is an integral from a to b And then we'll just do the antiderivative of py with respect to y. So that's just p of xy. Where, again, now these are limits on y. So y is going to go from f1 of x to f2 of x. And then there'll be a dx when we're done. So there's the p dx. Are those line integrals? They will be. We've got to do our substitutions here. So next we'll go from from C to D, and we'll have a Q of y2, or sorry, G2 of y, comma y, minus Q of G1 of y. Probably should make this, let's just do this, no, that's fine. G1 of y, y. So all of that will be dy. And then minus integral from a to b of, this will be p of x comma f2 of x minus p of x comma f1 of x, and that'll be one more parenthesis, that'll be dx. Now these are starting to look like line integrals because you can see the y coordinate is constrained to a curve. Y has to be f2 of x or f1 of x. So my y coordinate is being constrained to a curve on the second integral, and on the first one, x coordinate is being constrained to a curve. So these integrals are taking place over points on these curves. Any questions? Okay, now what I want to do is I want to do a little trick or two here. I want to say this is an integral from C to D of Q of G2 of y comma y. This would be a dy. The next, I'm going to change the order of integration and make it a plus. The integral from D to C. See how I change the order? Makes the integral positive. This will be Q of G1 of y. Comma y, dy. Okay. Trying to make space. Okay, minus the other integral. This would be, let me see here. What I want to do is write the second one first, and that'll be a plus. The second one is an integral from a to b of p of x comma f1 of x, like that, dx. And then the next integral is a negative integral from a to b, which I'm going to make into a positive integral from b to a. See how I'm switching the order of the limits? And then it's p of x, comma, but now I'm on f2 of x. Like that. And again, I need some space, so give me a sec here. So that again is a dx. Okay, so what I kind of want to do here is I almost feel like I want to copy this curve. I'm just going to get this picture here and maybe bring it down just to make sure we're all paying attention to what's going on here. Okay, so the first integral has x, it starts with x on g2 of y, and it goes from c to d. So that's the right curve, bottom to top. Okay. Okay. And then on G1, the next part's on G1 of y, which is the left curve, but notice it goes from top to bottom, right? Because it goes from D to C. So this is the left curve. Top to bottom. Okay, G1 is the left curve, and it's going from D to C, from high to low. So that these together make a counterclockwise orientation on C. Okay. I'm going to pause and see if I can see any questions here. So on the right, it goes bottom to top, around the right side, and then you get to the next integral, and it goes from top to bottom on the left side. Now on the next two, we're on f1 of x, where x goes from a to b. f1 is the bottom curve. Left, x is going a to b, so bottom curve, that's left to right. Okay. And the next integral is on f2, which is the top curve. And it's going from b to a, so that's going backwards, so that's from right to left. And again, on the bottom, you're going left to right, top right to left, that's going in this direction. And again, it's a counterclockwise orientation, which is why the theorem requires a counterclockwise orientation. Okay, any questions about that? So both integrals are integrating over the curve. They're both counterclockwise. They are therefore both line integrals. So you can see that the first one is just a line integral over C. And since you're on C, it's implied that X will be G1 of Y and then G2 of Y. We can just say Q of XY and dy here. So those two together make this integral. Plus the next integral, where it's P of X, and then Y is F1, and then later it's F2 as you come back around. Altogether, that's just Y. So it's P of XY, where Y changes from one curve to the other. It's over C. Both of these are closed loops, and they are both going counterclockwise. Okay. And now the second one is a dx integral. Okay, so then the shorthand is like this. Integral over C counterclockwise, we just write Q dy plus P dx. And I hope that's what Green's theorem says. Yeah, that's okay. Technically, it's this P dx plus Q dy, which is just F dot dr. Okay. I'm going to pause there and see if anybody wants to throw a question out. Have we not? We haven't taken a break, have we? So we better take a break, and then I'll do an example of this. So let's let me pause my recording here. So I can't remember how. Here we go.
Professor, your mic is muted.
I'm so ashamed of myself. Thank you for bringing it up and helping me. So I wanted to talk about non-convex regions. I'm going to do a slightly different approach here. So I'm just going to cut this region like this. And so this is still my curve C. Now, non-convex, the technical definition of a convex region is that it contains all of its line segments. So like this segment from this point, both of these points are in C, but the line segment from one point to the other is not completely contained in C, and that's what it means to not be convex. Okay, now, when we cut C this way, and maybe we could have one curve on the right and call it C1. Hang on. So this whole curve is just C, but on the right, I think I'll do a little C1. And on the left, I'll do a C2. oops, counterclockwise orientation like this. But it's not convex. So what I'm going to do is a little cut here, like that, and separate this. Oops, top's not cut. I don't know why. Let me try it again. Okay, try again. Okay, that'll work. Okay, so we're going to preserve the orientations where on C2 it goes down and on C1 it goes up. But then how about I do, I'm going to use P1 here and P1 on the other side too. I guess we could just do P. And I meant P to stand for path instead of curve. Doesn't matter what it stands for because we'll just use a P. Okay, and so on the first P, because I need a counterclockwise orientation, the orientation is downward on P. But with a counterclockwise orientation on the left side, the orientation has to be upward on P. Okay, so I would just say consider C, which is equal to the union of C1 and C2. Okay, illustrated here. Non-convex regions can always be cut into convex regions. And if orientations are preserved, I just note the following. I would say that a line integral along C with a counterclockwise orientation of, let's say, f dot dr. Okay, this will be equal to the sum of the two line integrals, including P. And then I want to ask you guys why this doesn't end up being bigger. So this will be equal to this line integral of C1 union P of f dot dr plus the integral of still counterclockwise of C, let's say P union C2, just to kind of make it look interesting. P union C2, counterclockwise still, of f dot dr. These are equal because the line integral on, well, I don't want to say. Can anybody tell me why those are equal? I mean, the sum of the two integrals has a much longer curve, right? Because you're adding p into all of this twice. So why doesn't the why doesn't the value of the total line integral get bigger? It's because the p parts cancel. So it's because if we do the line integral along p with an upward orientation, this is the negative of the line integral on p with a downward orientation. Okay, so the line integrals on these cancel. Those parts cancel when you add them together. Okay. So Green's theorem is true for just the curve C because it's true when C is broken up. So it would be both true for C1 union P and also P union C2, both of which are convex. Okay, so just, the theorem talks about convex regions, but it also works for non-convex regions just because of this idea that non-convex regions can always be cut up into convex regions. And then when you add up all those line integrals, they add up to the original line integrals. So Green's theorem will work on all of those little convex regions and therefore will add up to the total. Okay, so there's that. That's just kind of one note. There's some more I want to do later with Green's theorem. But let's do a quick example of the theorem just to show that it works. Okay, any questions to this point? All right, well, let's do an example. Okay, so we're going to evaluate work over the field F, which is this PQ thing, equal to the first component is going to be the square root of x squared plus 1. And the second component is going to be tan inverse of x. Okay. So that's almost too easy because there's no function of y. I feel like I'm cheating. Okay, so we're going to compute the work, and then we want to do this using Green's theorem. To convert to a double integral. Okay, so let's go ahead and begin. So if we have a double integral of, sorry, if we have a work integral, oh, and I have to give a curve, don't I? Okay, here's my curve. Okay, so the top is y equals 1. The left, or so the right is y equals x. Of course, that's on the right. On the left, it's x equals 0. And it has to have a counterclockwise orientation. Like that. Okay, inside is region R, and on the outside is C. And again, we say C has to be piecewise smooth, which means it's not smooth everywhere. It's just smooth in pieces that, and there's only a finite number of pieces. Obviously, it needs to be continuous or it won't enclose a region. Okay, so there's my curve C. If you care, this point is 1, 1. Okay, and so let's jump right in here. If we're going to do f dot dr, Green's theorem says you can convert, and by the way, this would take 3 integrals because curve C is broken into 3 parts. But this might be easier to do as a double integral over the region inside of qx minus py. dA. Okay. So maybe just off to the side, remind the, I'm above here. Qx will be 1 over 1 plus x squared. Remember, q is the second component there. And py is going to be 0. Okay, any questions about all that? Okay, well, that doesn't seem too bad. So we're going to have a double integral of qx, which is just 1 over 1 plus x squared. Makes sense to do dy first and dx. What's the lower limit on y? Thank you. Q of x. I think you mean q with the subscript x. Is that right? Q sub x? No. No, these p and q are independent of each other. So This first component is P, and the second component is Q. And when we say Qx, we just mean the derivative of Q with respect to X. Okay. That's all. And Py is the derivative of the first one with respect to y, but it has no y, so that derivative is 0. Okay, good. Okay, and then again, limits on y. Somebody already said the lower limit on y is x. That is true. Upper limit on y? Anybody got an upper limit on y? 1, good. And then x will go from 0 to 1. Okay, any questions? Okay, so we're going to zip this out real quick. So with respect to y, we're just going to have a y here over 1 plus x squared, and y will go from x to 1, and then we'll go dx. So we have an integral from 0 to 1, y will be 1, then it will be x. So we'll just have a 1 minus x, and this 1 plus x squared kind of goes for the ride. I think I have to split that into 2 integrals to evaluate it. I don't think I'm smart enough otherwise, so I would say integral 0 to 1 of just dx over 1 plus x squared. And then minus the integral from 0 to 1 of x over 1 plus x squared dx, like that. And so in this one, I guess u, this is going to be a natural log, right? So u is going to be 1 plus x squared, and 1/2 du is going to be x dx. And so that first integral we're going to have, what's that first integral? I know you know. I don't know, just to practice. What's that first integral? Okay, took too long. So you know, I know you know. Tan inverse x from 0 to 1. Okay, the second integral I'll just write as the integral of 1/2 du over u. Okay. And when x is 0, u is 1, and when x is 1, u is 2. Okay. Any questions? I think we're almost done here. So tan inverse of 1 minus tan inverse of 0, which is 0. And you're going to have 1/2 ln, so that's minus 1/2 natural log absolute value of u from 1 to 2. Okay, what's tan inverse of 1? Anybody? I'm going to make you answer this time. I guess I can't, actually. I'm going to say a little prayer that somebody answers. Ah, pi over 4. That makes me happy. Thank you. Pi over 4. You can have a minus 1/2 natural log of 2. Like that. And of course, the natural log of 1 is 0. So I think I'll just leave that with a reminder over there. Okay. Any questions? And so that's the that's how much work it takes to move the object around the curve that I drew wherever the curve went. Pretty good. I mean, it's right here. So the object we're moving has been moved around that curve through the force field described above. And the amount of work was pi over 4 minus 1/2 log 2, and that would be in joules or foot-pounds. Okay, any questions? Let's ask Green's theorem. Um, there's a side issue here. How are we doing for time? It's 8:07. So yeah, we can at least finish this. I think we may finish early today, but no promises. We'll see how this goes. I meant to do more than just this section today, but that's the way it is. Okay, so here is, remember Green's theorem says that the integral of q dy, my bad, plus p dx over some closed curve C is equal to a double integral of qx minus py. dA over the region R contained by C. So that's Green's theorem. And I guess something to note is that if qx minus py turns out to be 1, then this integral will be a double integral of just 1 dA over R, which of course is the area of R. So this is an interesting idea that you can compute an area by just looking at the perimeter of a region. I mean, C is the perimeter of R. And there's some sort of an analysis that you can do on the perimeter that gives the area of any region in the plane, of course. And that turns out to be sort of useful, and it leads to a formula. I don't know if you remember, but at the end of chapter 15, I did an example where I had a kind of a complicated polygon that I found the area of. And I found the area of the polygon just by looking at points on the perimeter. And that's a specific case for what I'm about to do. Okay, so so I can think of lots of ways for qx minus py to be 1. Here's one. Qx could be half. Py could be negative a half. That's probably a more complicated way. There are easier ways for this to happen. Okay, there you go. So it's a half plus a half now. So that would mean Q would be 1/2 x, and P would be negative 1/2 y. And so the integral over C, closed curve, of Q dx, that's 1/2. Well, let me go ahead and write it all out here. So this would be Q dx, sorry, Q dy, plus P dx. This would be the line integral around C, counterclockwise. I would have a 1/2 x dy minus 1/2 y dx. This would be the area of R. that can be rephrased a little bit. So there's my C. Gotta have a counterclockwise orientation. Okay? So we would have to say if C is piecewise smooth, containing R, I should say continuous, and containing R, then the area of R, here's an integral that will give the area of the weirdest of regions. So if you think about it, you've done a lot of areas of things with single integrals, but they've always been shaped where it was between a bottom curve and a top curve, basically. You've not done an area of a very weirdly shaped region like this, except for if you cut it up into lots of little regions. So this will allow you to find the area of any shaped region without cutting it up. You just have to have some sense of what the boundary of the region is. Okay, so you would say the area of R is just a line integral over a curve C, again with a counterclockwise orientation, very important. Okay. And I should put the 1/2 out front, so forgive me while I move that. Put a 1/2 out front. And it's just x dy minus y dx. So that's crazy to me. And at first I used to think, oh, that's not that big of a deal, but now I think it's really helpful. And like I mentioned to you that this turns into the polygon formula. And I, like I said, I know people in construction that basically, without knowing it, they compute areas of polygons where this theoretical statement is a generalization of their approach. And they have no idea about calculus, but they're using the consequence of this theorem to compute areas of polygons. And you need to know the area of a polygon, you know, if you're pouring a cement slab or something like that. And I think I mentioned to you guys, the guy who showed me this was someone who used to pour sidewalks. And he uses the generalization of it. All right, well, that's one thing. So I want to go ahead and do a quick little example. We have time, so I want to know what is the area of the ellipse bounded by x squared over a squared plus y squared over b squared equals 1. And maybe you know the formula for the area of an ellipse, but this is a really clever way of evaluating it with a simple process. Okay, first of all, you need to parameterize the ellipse. So you may remember I've told you the parameterization for an ellipse, R of t, has to be a cos t and b sine t. And you can note that x squared over a squared is just a cosine square, right? Plus y squared over b squared, that's just sine square. And so that's equal to 1. Cosine squared plus sine squared equals 1. So that just kind of validates that this truly is the parameterization of the ellipse. Okay. Any questions? Gosh, I'm having trouble with my stylus. Okay. So, I think we can pull this off. So when we say x, we mean a cos t. And when we say y, we mean b sine t. Just keep that in mind. If R is the ellipse, beautiful. That is less than perfect. It's okay, I guess. And we need that counterclockwise orientation, so I'll spin it around like that. Okay, so the area of R, according to our theory, is 1/2 integral OC of x dy, right? Minus y dx, like that. Okay, so now we just got to make sense of what all this means. So I get to 1/2. That part makes sense. We'll make this into an integral. I think we're probably going to end up putting limits on here. X, maybe we should write down what dy is somewhere. So once again, I ask your forgiveness. And just take a moment and say what dx is. This is x prime dt. So this would be negative a sine t dt, and dy is y prime dt. So that'll be b cos t dt. Okay. Okay, so I think we're ready to go. So 1/2 out front, then you do an x dy. So x was a cos t. Dy is b cos t dt. T is ranging from a to b. Then minus y, which is b sine t, dx, which is negative a sine t dt. Now notice that's one integral with two dt's, which is just so uncomfortable, right? But of course, we're going to put a 1/2 and an AB out front. Did I have the integral go from A to B? That's just hilarious. What are the what are the limits on T? This is like a circle, right? So T goes from 0 to 2 pi. So forgive me while we put a 0 to 2 pi down for the limits on time. Okay, so we got the 1/2 AB integral from 0 to 2 pi Okay, and inside all that's left is a cos square t plus sine square t and dt. Okay, so that's just one. And so you end up with AB to 1/2 AB times 2 pi. Which is pi AB. And that is the area of an ellipse. And you'll never find a cleverer formula for finding the area of a two-dimensional region with any perimeter at all. Or I should say any boundary at all. It's just simple, it's clever. You know, I mean, if it's broken up into a bunch of line segments, that could be a bummer, but there's actually a super way to do it, super easy way to do it with line segments as well. Okay, does anybody have questions about that example? Now, you have a homework problem, number 21. I'm waiting, I just want to wait one more time. Any questions out there? Okay, so this one was sort of interesting. If somebody asked you to do the area of this polygon, that could be bad, right? And I'm saying, no, it's easy. So here's R. Okay. Here's, let's say X. Oh, I need to move it over. Isn't that beautiful? It doesn't matter what shape you draw. Draw any shape you want. Okay. So that's X1, Y1. This is X2, Y2. And so on, right? X3, Y3, etc. Okay. And notice I'm going in a counterclockwise orientation. If you go clockwise, what do you think will happen to the area? Anybody? Yeah, the area comes out negative if you go clockwise, which is not the end of the world, right? Who cares? But it changes the sign of the answer. Okay, any questions? The second to the last point here, right there, I think I like to call it X sub n minus 1, Y sub n minus 1, like that. So that the last point is actually the first point. Okay, so this X1, I still need more space. So I like to close the polygon so that X1, Y1 is the same as X and YN. Does that make sense? So I think there's actually only n minus 1 points. Okay. Now, I would break this up into pieces. So you're going to have a curve 1. There's going to be a curve 2. There's a curve 3, a curve 4, etc. Okay. The last curve here will be curve n minus 1. Got it. Let me put my little arrow back here. Okay. And so, and we know for sure that the area of R is 1/2 integral over C of x dy minus y dx. Let's make that. And guess what I'm getting at is this would be 1/2 times the sum of the integrals over Ci of x dy minus y dx. And I guess I would go from 1 to n minus 1. Like that. I think I would just do one of these. Okay, I mean, what is it? How's it come out for just one of these? So for curve CI from let's see, CI will go from, it'll go from XI, YI to XI plus 1, YI plus 1. Like that. Okay, then what would that integral look like if we were just doing the integral over CI of 1/2? Well, I guess we, I'll go ahead and move that in. So then you'd have the x dy minus y dx. Well, you'd have to parameterize CI to do that. Okay, so basically CI would be parameterized the way we parameterize any line. Okay, you'd have like an R of t equal to like an R0 plus R1 minus R0 times t. That's how we parameterize lines. Okay, so R0 is this xi, yi. Like that. Plus R1 minus R0, yuck. Okay, so this would be an xi plus 1 minus xi, comma, y, I plus 1 minus yi, and that's times t. And you'd have t range from 0 to 1. Well, actually, let's combine these, so no bad, before we write that last thing. Okay, so we'll have xi plus xi plus 1 minus xi. That's times t. Same thing with y now. So, oops, comma, there'll be a y I plus, I don't know why this is taking more space than the last one, but it is. Yi plus, so we're going to have a yi plus 1 minus yi, and that would be times t. Okay. Okay, so this thing right here is x, and this thing here is y, and we may as well say dx is going to be x sub I plus 1 minus x sub I. Yeah, it's the difference of two x's, dx. Totally get that. Times dt. And dy will be likewise y I plus 1 minus y I times dt. And it's almost to the point where you could just plug and chug this. How are we doing? It's time to go. What's this integral? Okay, this is homework. Number 21 in this section, which I don't even know what section we're in anymore. This is 16.4. Okay, so you'll see that in your homework, and it's an interesting problem, and maybe I'll finish it next time. Maybe I won't. Maybe I'll let you guys finish. Anyway, I'll see you guys. Have a great couple of days. Again, I'll have those tests finished in the morning, and there's a couple that I need to look at again, but I'll be talking to you more about tests on Wednesday. All right, everybody, take care. And I should say, if anybody has a question, feel free to post, to chat it right now or post it. I can take questions now.